All right, we're back for another episode. Today I'm joined by Professor Lisa Olshansky, who is an assistant professor in the Department of Chemistry, but kind of studies bio-inorganic chemistry at University of Illinois, Urbana-Champaign. And we'll get into her research into some good time because it's really, really interesting stuff. Studying, metal complexes capable of undergoing like triggered conformational changes. Like I said, we'll get to a good time, but I think we'll start with your background a little bit, just so people can get to know you. I know you did your undergrad in UC San Diego, or at least you transferred there anyway. So I guess I'm curious if you kind of grew up in the San Diego area, possibly.
No, I actually grew up in the Boston area.
Wow. Okay.
And basically, yeah, I kind of I really hated high school and had no plans to go to college at all.
Really?
Um, and uh, and and I was just traveling after high school and kind of lived all over. I lived in Mexico for about a year and working,
Wow.
obviously, and having lots of adventures. And ended up living in San Diego. And I started taking classes at community college when I was 25 at San Diego City College. Um,
Wow.
so that's
This is.
kind of why I ended up out, or how I ended up there.
I was gonna say this sounds like this is definitely. I obviously didn't know this, so this sounds like a very interesting story for another time to hop into
Yeah.
how you got there. Um, yeah, I'd love to do that. Do the podcast on that. How you arrived at
I
San
mean, you
Diego and
get
all
to
those
the end of the
stories.
highway in San Diego, and
Yeah,
yeah, I think so. A lot of people end up, where a good percentage of people end up in San Diego because that's actually where the highway ends.
yeah,
It's the corner of the country and to the ocean, and then it's a pretty nice place to stay. So,
yeah. I mean, I know San Diego is super nice because I mean, a lot of the U.S. veterans and like their military is there, so it's like that's where a lot of those like the training camps are. So I know it's like heavily populated with like veterans and
yep,
like SEALs and army soldiers. Um, Unfortunately,
yeah.
the Chargers left. The Padres, I don't. The Padres are kind of iffy. There's no really sports culture, but I assume like San Diego is it's a very beautiful city, though. I've never been there, but I can only assume that you once you go there, you
Yeah,
probably
it's
don't want to leave.
gorgeous. I mean, the weather.
Yeah,
Yeah,
I guess.
yeah. But yeah, I
A
mean, I took a lot of classes on the bases with with people who are active military. Um,
mhm.
I had to take a political science class, for general ed, and it was kind of cool to take it in a class like so mixed with, myself who's not in the military or really from that background at all, with, fellow classmates who have kind of a really different perspective on politics.
Sure.
So yeah, it was cool.
I guess a natural question is like how. So you attended community college first. You've taken a few classes here and there, but I mean, how did you get into like chemistry and bioinorganic chemistry? Then, like, how did that kind of come about? Like, were you taking chemistry classes? Did you know what you really wanted to do at that time, or you just kind of taking
Yeah,
whatever?
I was trying to find a cure to cancer. So before I started school,
Beautiful start. It's a
I was
beautiful
like
start.
go to the library trying to, yeah, yeah. And I, was reading and was reading a lot about like natural products and like, these medicines that indigenous groups in like uh, have have discovered from like natural plants and isolating these natural products and then like the overlap of that with chemists then doing total synthesis who are isolating natural products and using them for drug development. um, and I really just felt like it would be very helpful if I had a systematic way to learn all of this chemistry that I was reading about. So I went to the community college and I took the assessment test because I wanted to take a chemistry class, but they were like, well, first you have to we have to see if you can do math and writing and stuff. And I tested into only eighth grade level math. So I had to start off
Mm.
like So it was much more than taking classes here and there. Like I took classes at San Diego, well, 5 years, I guess, at City College.
Hmm.
I took all the classes I could, but basically I had to start with like fractions and like
Okay.
just simple algebra and go through every part of high school math and then college math. And then I basically, and then also once I could take the chemistry classes, I took it and I just kind of loved it. My first, the first summer I took a math class and which was that like, pre high school class um, and an cultural anthropology. And it was
Hmm.
sort of like these two things I had been reading about like indigenous cultures using medicines, natural products, and then also like the math part to get into the chemistry of the natural products. And I felt like the cultural anthropology was cool, but like I totally didn't need a teacher. Like I could just read the book.
Yeah.
I felt at the time I was probably a little arrogant, but the math on the other hand was like really helpful to have a teacher
Sure.
and guidance and practice problems and all that and to go over stuff. And I just kind of loved it, and I loved like doing my homework. And I was really surprised because I had hated high school so much, but
Mm.
I just ran with it, and then loved the chemistry classes I took. I had an awesome organic chemistry teacher there, Dr.
Yeah.
Ram Guru Murthy, who we still are connected. And yeah,
Look how far you've come.
I don't know. Yeah. I remember. So like the day so I was taking a lot of night classes because I was working as a window cleaner all this time. And
Yeah.
one night I was in the organic chemistry, the lab part of the class, and I was leaving the lab. It was like 10 at night on like a Tuesday or something. Of course, I was exhausted. I worked all day. And I was leaving the lab, and Dr. Guru Murthy was like, have you asked me if I had ever considered going to graduate school?
Mm.
And I totally laughed in his face. It was probably very rude. But I was like, that's ridiculous. Like, how can anyone be in school for that long? Like, how can anyone afford it? Blah, blah, blah. I mean, I didn't say that out loud. I just kind of laughed.
Sure.
But actually, like, yeah, then I learned, he kind of sowed the seed because then I learned a little bit about it and realized that you get a salary and that this was like actually a career that I could
Yeah.
maybe like good at. So yeah, I kind of just ran with it.
That's really, I mean, quite honestly, it's a bit kind of inspiring, honestly, because you really have a non-traditional path to go into graduate school. Um, do you feel like, because you definitely, obviously before attending graduate school, you had been working, all day and then taking classes at night. Do you feel like that prepared you really well? Because like you probably learned so many life skills, right, before even like entering graduate
Yeah.
school. So I don't know, like, I mean, that must have been really fascinating. It's definitely a really fascinating experience for sure.
Yeah. I
Um,
mean, it was super helpful. I think, I mean, as you know, graduate school, a lot of it is about time management and, or a good, being able to manage your time is very helpful for grad school.
right.
And, yeah, I for sure had an advantage. I also had the advantage that like, I really knew what I wanted.
Mm,
I had, done all the partying before I started college. So I wasn't like in college to learn who I am and like party. I
right.
was in college to take classes. And
Mm,
and so I think that was also an advantage. Um and I'm really glad I didn't. I mean, my family was really upset when I graduated high school and then just pieced out. They, thought I'd never go to college and this and that. But I'm glad I listened to myself because if I had gone, I wouldn't have taken it seriously. I would have gotten bad grades, and you really can't
mm,
do it twice. Like I ended up with fellowships and scholarships all the way through and never paid. I paid for my first semester at community college, it was $13 a unit at the time.
wow.
But then I got scholarships the rest of the way because I had kept up a 4.0. So which I could
Wow.
have never done. If I had gone after high school, I would have been for sure partying and learning, growing and learning who I am as a human.
Yeah, that is super fascinating to
Like,
hear um because yeah, definitely, like, you always hear students going right from basically virtually right from undergrad, or maybe they have a year, maybe two in industry, and then they go to graduate school. So, like, I mean, the fact that you did all this traveling right out of high school, like, is super. I mean, that's just unorthodox. Like, I don't know. I don't even know how many other people have done that. At least in academia, anyways. So that's really kudos to you. It's really cool that you had that experience. Um,
thanks.
so
Thanks.
now you mentioned that when your advisor had mentioned graduate school, you kind of laughed at his face, whatever. But what was kind of the turning point, like when you were like, oh, this is actually kind of serious, like, and how how did you kind of decide, like, what kind of chemistry you wanted to pursue?
Yeah, good questions. So turning point for grad school was really so my that same guy, Dr. Gurumurthy, on a Saturday. So City College was downtown San Diego, near where I lived, and UC San Diego is up in La Jolla,
Okay.
which is it's about an hour and a half bike ride, or about an hour bus ride, or a 20-minute drive.
Yeah.
He drove me on a Saturday and showed me. So at City College, I don't know if this is still true, but we didn't have access to the scientific literature
Okay.
at community college,
Wow.
like how you can just log in at the library.
Is that a sci hub either?
You can go to UC San Diego. So, I mean, at the time there was
No.
no access. I don't know how it is now.
Yeah.
Because you
You
have to
wouldn't know
pay for
anything
all
about
those
that. Yeah.
subscriptions. And
You wouldn't know anything about that, would you?
um,
Playing for the free academic,
about what?
about the free academic journals through Sci-Hub.
Oh, I mean, at the time, also that wasn't really a thing.
Yeah,
I
it wasn't a
mean,
thing. I
there's
was
a
just like joking
couple
around.
open access.
Yeah.
Okay. Um, Sorry, I have no idea. I'm old. But so yeah, so he drove me on a Saturday and drove me up to La Jolla and took me to the library and showed me the chemical literature.
Mm.
And I kind of just like my world got a lot bigger. And I also started going up there. Like I realized, somehow figured out that, all these seminars that we have in our different departments, they're all free and open to the public.
Yeah.
And so I started like showing up at seminars, even before I transferred. Um, yeah, it's kind of funny. I saw someone. So, okay, I had dreadlocks, and a
Hey.
nose ring, and, I was a little rough around the edges. I think I still am a little bit, but I showed up to someone's thesis defense at the Scripps Research Institute.
Okay.
Someone named Scott Snyder, who's now a
Oh,
professor
well.
at Yale, I believe. Um,
No big deal.
and I looked a little out of place. So I didn't realize that the thesis defenses were so much smaller than like regular seminars where I could kind of just show up in the back and like listen in.
Yeah.
But so I went to this thesis defense, and it was a little, it was, I mean, whatever. But I met Scott Snyder last year at the Cottrell Scholars Conference out in Arizona. And I was like, hey, do you happen to remember your thesis defense? Was there like a weird looking dreadlock girl sitting in the front row? And he was like, now that you mentioned that, that sounds familiar. And I was like, bro, that was
That's
me.
crazy.
Which is, yeah. And so I kind of like, well, once I started discovering, so really this teacher, Dr. Gurumurthy, really kind of like introduced me and showed me that this world existed. And then I was reading papers and going to seminars and was like, pretty hell bent on getting myself in a lab once I transferred. And then I was like working around grad students and kind of had realized, that you get paid to go to grad school and that this
Right.
is like a reasonable option. Yeah.
So after you had,
I forget the other question.
I don't remember, but oh, I guess it was gonna be like how did you like into bioinorganic? But we'll touch on that a little bit though, because I guess because
Oh,
after
okay.
after undergrad you went to MIT. I guess what I'm curious about is because you did graduate school at MIT. What did you do there? But also, I'm kind of curious. Like, I don't know if you still talk to your parents at the time, but like, yeah, I'm gonna go graduate school at MIT. Like, I don't know if they like kind of believed you or like I don't know. It's kind of I'm interested to hear that.
Yeah, it was pretty funny. I wasn't super close with them, and especially not my dad. But my
Sure.
dad was a physicist, and so he was like pretty blown away. I didn't really, yeah. When I showed back up in Boston where they were, and I was like, "Yeah, I'm in a PhD program for chemistry at MIT." Like, his mind was pretty blown.
That's crazy.
Um, but yeah, so yeah, I guess in terms of my like scientific evolution, I started off with this, super excited about organic synthesis and natural product synthesis. And I mean, as in most undergraduate chemistry programs in the United States, you don't learn inorganic chemistry until like the very end often
Mm-hmm.
there's a lot of prerequisites for organic that you start early and really I still love mechanism and pushing arrows and
Sure.
um predicting organic transformations. And that's what I went to MIT. I applied to grad schools and applied on the basis of organic synthesis and total synthesis professors. um, and I went the summer before grad school and worked in a total synthesis lab. And I loved it. And it was, kind of exactly what I had been wanting to do. But I
Mm.
also, like, at that point, I had taken all of the grad level organic classes at UC San Diego and had been kind of obsessed with organic synthesis for however 5 years or something. And I like almost knew all the named reactions, but at that first summer I was like, I'm gonna like know all this stuff pretty soon. And I love it, but I also want to learn about all this other stuff like
Right.
you know um math and spectroscopy and some of the things that I had learned in my very last classes at UC San Diego, inorganic chemistry. Um, and I was got pretty inspired. I was kind of secretly inspired by this way before I accepted the admission offer at MIT, but I was pretty excited about Dan Nocera's research in
Mm.
energy science application
Right.
in energy and so I kind of made this like pretty bold move because really didn't have a background in inorganic chemistry. But I kind of jumped ship and I decided that I would try something new and join an inorganic lab and get my PhD in inorganic chemistry, even though that was totally not like uh I had no background in it. Yeah, and I had a super strong background in organic synthesis.
Yeah.
So, but I followed my heart instead of like the logical thing that you should do, which has always
Wow.
kind of steered me right in my life in general. So,
Yeah. I
yeah.
mean, look, I mean, you gotta follow your gut feelings sometimes. I mean, what did your old organic advisor say when you're like, yeah, I think I'm gonna go pursue like materials basically in inorganic chemistry? Was he? I mean, was he like excited for you, or was he like, oh, I don't know?
The one that I worked in at MIT in the summer
No, no, the your
or
old at UC
college.
San
Oh,
Diego. Yeah.
the I didn't talk to anyone about this decision, and I think
Yeah.
that was a naive I think I should have. And so like, if there's any students listening, like I definitely suggest that you talk to people about your decisions. There's people that can help you make them, and or at least just help you understand the repercussions of them, maybe.
Mm-hmm.
Yeah, like I think it's a combination of you follow your heart, but because that's the thing that's going to get you out of bed every day in grad school
Right.
to go do research. But yeah, I didn't talk to anyone. I was just
Okay.
like, and which is kind of, having carved my own like path through academia, I was really clueless and still am a little bit, about how it all works and like, how to navigate these things. And it's a
Right.
lot of just figuring it out for myself
Mm-hmm.
sometimes.
I mean, you made the right
Yeah.
choice because obviously, like you've been kind of, I mean, more or less an individual, taking your own individual things up until that point, right? So, like, why not just keep doing that? And it just worked out so far, right? So, but out of curiosity,
Yeah. And I for sure have no regrets.
yeah, out of curiosity, did you cross paths with Professor Thomas Tietz, or was he? Does Thomas Tietz ring a
Yeah.
bell?
We were lab
Okay.
mates for like 4 years.
Oh, okay,
Yeah.
that's sick. Okay,
Teats.
yeah, he's because he's now a professor here at UH, so he's actually one
Yeah.
of like professors here that I know. So I was like curious. Um,
Hi, Tom.
uh, but okay, so then I assume then you were in Nocera's lab for MIT, right? Or okay,
Yep.
yeah. So what did you? What was
Yeah.
kind of like?
Well,
What was your projects that you worked on?
yeah. So my first project was a little bit crazy. I was collaborating. Dan would agree. I was collaborating with a biology lab who studied cyanobacteria in the oceans. Who like would go
Oh,
out and collect cyanobacteria
that's
and
pretty
study
cool.
their ecological and biological and a lot of like they did a lot of DNA analysis of like these cyanobacteria have like the smallest genome of all organisms, and how does that work? What does this minimal genome look like? But I was taking these cyanobacteria and trying to purify photosystem 2 from them. That's the enzyme that converts, uses sunlight to split water into oxygen and protons and electrons. And then and so I was doing that for like 2.5 years.
Mm-hmm.
And then Dan got his NIH grant rejected on
Oof.
his project that was in collaboration with Joanne Stubby working on ribonucleotide reductase. And so he asked me, and part of the reason it was rejected is that they hadn't made enough progress. And so he asked me to jump on to that project, at least temporarily, till he could get his grant renewed. And then I could choose whether I wanted to stay on it or go back to photosystem 2. And so then I started working in Joanne Stubby's lab on, we were trying to study proton coupled electron transfer in this enzyme
That's
that
where it all
has this
begins.
long range. Yeah, it's a long range electron transfer, and each step has a proton transfer with it. It was like amazing. I started learning so much more, and like Joanne's just super inspiring and passionate about chemistry, and the system was super interesting. And so I think that's really where, well, I guess I also loved the photosystem 2 stuff too. So I don't know, but it definitely like elevated my, just by interacting with her in her lab instead of interacting with biologists who just
Yeah,
kind of weren't thinking about the same things as I was. So I
sure.
had more people around me to talk science with. Um, it really sort of accelerated my learning and result and research progress.
Sure. Were there any
So yeah,
like
so what
big?
I was working on, those.
I was gonna say, like, were there any like big kind of like takeaways from your experience there, or like like um any big takeaways like from the research you had done?
Um, yeah, there's a few. So um, I was studying. I was doing a couple different things. One of them was attaching a photoox. So ribonucleotide reductase has this multi-step PCET mechanism.
Nope.
But the whole PCET process, and the reason why Dan was interested in that is because um, proton coupled electron transfer, if we can figure out how to handle PCET processes and facilitate them in a controlled way, the way that our ribonucleotide reductase does, then we can use that in energy technologies and strategies for energy conversion and mimicking things like photosynthesis. So it's all kind
Mm,
of tied together. But the problem with studying this enzyme mechanism and the PCET steps in it is that the rate determining step of catalysis is a protein structural rearrangement or a conformational change. And that masks kinetically all of the PCET steps. So we couldn't study them. And so I was attaching a photooxidant to ribonucleotide reductase to, instead of relying on the normal conformational changes that happen when a substrate binds
mhm.
to trigger catalysis, I was photo triggering these catalytic steps in the enzyme.
Okay.
So that we could basically see them so that they weren't masked by the conformational change anymore, by the slow conformational change.
Okay.
Um, so yeah, we were able to measure the rate constant for substrate activation and set sort of upper bounds for that. There's the first step of substrate activation in the active site is a hydrogen atom transfer, and we were able to like set bounds on the KIE for that. And then I was basically modulating the thermodynamics of all these PCET steps by replacing tyrosine residues that were active in doing proton and electron transfer with fluorinated tyrosines, so unnatural
Sure.
amino acids that have different redox potentials and different pKa's. And so then we could look at the effects on the rate constants for PCET. Yeah, that was one of the things I was working on.
That's
And there were
was
also,
were these things like kind of easy to
yeah,
study? Were they kind of easy to study? Like I don't like how do you do it? Uh,
no,
what's like the practical
it's
or
hard.
how do you do it practically? Like what do you have to do?
So you have to first you have to purify an enzyme that converts phenols into tyrosines. And so
Okay.
you could then feed that enzyme um, fluorinated phenols, and it'll make fluorinated tyrosines.
Okay.
And then you have to express your enzyme or ribonucleotide reductase in the presence of that synthetically prepared fluorotyrosine. So you have to make that, you have to purify it. Then you add it to E. coli when you express the enzyme, the ribonucleotide reductase, and it so that it can get incorporated. And then you have to purify ribonucleotide reductase. But ribonucleotide reductase has two halves, and so you have to purify two different enzymes or two different subunits of it separately. And then one of those halves has a bunch of cysteine residues that are really important for catalysis. And so when you purify it, you have to take great lengths to make sure that all those cysteines stay reduced and they don't get oxidized by air.
Okay.
And then you have that enzyme, and then you have to purify the other half, and that half has a metallocofactor. So once you purify it, you have to then bring it into the glove box and reconstitute the metallocofactor using iron, and then, so then you have your active two halves. And then you have to attach the photooxidants. You have to synthesize a photooxidant and attach it to the protein. And all of these things you have to characterize along the way.
I was
And
gonna say
then
Jesus.
you basically go and fry this thing in a laser. And it takes like a couple hours to ruin like a month or 2 months worth of
Oh
preparation
my
in lab.
God.
But we got some data. So yeah.
Were there, so let me ask you this, because obviously, like, I mean, I'm sure this took a long time. If you're a new student, like learning all these techniques and like all the little like techniques that goes into making all these products, like, I mean, how, like, I mean, how did you get yourself through that? Like, I'm sure like there must have been a lot of failures along the way. So how did you like keep going with
Oh,
this then?
um, you know, it's maybe a stupid answer, but I was just really excited to try it. And I mean, I'm not a person who, like, I've met failure a lot of times and had I guess I like, maybe it's where it helped to have a little bit more perspective as like an older graduate student. So I started my PhD when I was 29.
Right. Okay.
And I had some life experience, and like I was still so psyched to be there even when things were failing. I mean, there were definitely times when I was not getting enough sleep and was like a little bit unstable, but mostly I was just like super excited to be there and to be able to take part in research and to get paid to do research. So I don't know. I know that's really different from a lot how grad students see it now. Um, and I've thought, a lot about like, why was it so different for me? Like, is this you know, I don't know, but I was just kind of psyched to
Yeah.
try
No, I
and
mean,
didn't really expect things to.
like I feel like obviously, like you mentioned, you had all these life experience before being a grad student, so it's like, so you like, how do I put this? Like, there's more important things to life, let's say, than the science itself. So like bad science or like failure in science, as long as you're trying your best, it doesn't make you a bad person. So like maybe like you definitely had that in your mind. It's like I'm trying, it's not working, but like I'm not a bad
Yeah,
person, It's just like, and I guess that's kind of exciting to try this every day. So I definitely hear that for sure, you know.
yeah, yeah,
Um,
for sure. Not a bad person. I'm still alive. I'm like healthy, like
right.
hopefully, kind of, except for lack of sleep.
Yeah.
But
There's just more
um,
important things,
yeah,
like, you know,
perspective.
and
Yeah. I mean, I still remind myself of that now, when it's not so much, I guess, at this point, like that science isn't working, but that, because I think that's more something that the students kind of face day to day, right? Like I, as the PI, usually get like kind of like the exciting results.
right.
But you guys are like every day dealing with the failures. But there's other types of failures or hardships that happen at this level where I'm at. And I still, remind myself, like, I'm still alive. I'm still healthy. Like, my
Right.
career is not me. Like,
Right.
yeah.
You know, I mean, good science, like, really should not, you really should try and not let it like take over or consume your life. Like, that's how I feel personally. Like, I mean, try your best. If you're interested in the subjects, continue working at it. But just remind yourself that, like, if things fail in the science lab, it doesn't really make you a bad person. That's kind of the bottom line, I feel. So I definitely hear that.
Right. And
Uh,
you can be obsessed with, like, it can consume your life and you can be obsessed with it and passionate about it.
right.
But then, that doesn't mean, I guess, I don't know. Because I like to be obsessed. Like, I like it to be my life, even now. Like,
Mm-hmm.
I love this job and I put everything into it. But, you know, yeah, when things go wrong, like, you do have to take a step back and
Yeah.
remember the big picture.
Yeah. I hear that. Yeah. So, I guess for graduate students out there, just kind of be mindful of these things. Like there are sometimes more important things, and it's not an excuse to not be working diligently in the lab. But like, I don't know, just take a step back sometimes, and just take a deep breath. Like it's okay. Um, that's there's just more. There's some things that are just
Yeah.
more important in life. Your mental health, physical health. Because it's hard to do good science.
Yep.
If you're not
I
in a
mean,
good physical or
usually,
mental state, it's hard.
absolutely. Maybe impossible. I
Yeah.
usually, my students get their best data the day they get back from vacation.
Yep. Yep. Burnout's real.
Take from that what you would
Yeah.
yeah.
Burnout's real. So just be
Yeah.
mindful. Be mindful of yourself. I guess so. But after you completed your PhD at MIT, you went on to go do a postdoc at UC Irvine. Um, you know,
Mhm.
what was it kind of a natural progression to go to the postdoc? I mean, and at this point, had you begun to think about becoming a professor?
Yeah, good question. So I had never, like in grad school, um, I had never really thought that being a professor was necessary, like a career path. I really didn't think about the future that much. I was kind of just engrossed in my experiments, and
Fair.
which again is different, I think, from the current generation. And but that I just wasn't worrying about it that much. But it was Teets who is like obviously going to be a professor, and that my lab mates kind of had this more traditional background, and they speak differently than me and look differently than me and behave differently than me, and
Fair.
they kind of seem like the ones that could be professors. And so I never really thought about it. But toward the end of my PhD, I was just still so psyched about doing creative experiments, and I had ideas for future career research that I wanted to do, and just scientific questions that I was really excited to still continue pursuing. And so I started thinking about the possibility of becoming a PI. And I thought that's what I wanted to do. And applied for a postdoc position with Andy Borovic, and he said yes. And then I spent a couple months submitting some postdoc fellowship applications. But then I decided to push back my start date of my postdoc a little bit, by a couple more months, and I went on a trip. I wanted to
Sick.
put myself in a situation that was like totally separate from academia, to make sure that I wasn't following this career path. Like I kind of wanted to know before I started my postdoc what my plans were after. Like it's a postdoc is short period of time. I wanted to like have a plan of like where I'm going from there.
Right.
And I thought I wanted to go into academia, but I didn't want to like go in with blinders on, where, just because the only thing I've ever been exposed to is academia, that's why I want
Right.
to go into academia.
Mm.
So I went on this trip, which was my most epic travel adventure ever. I flew to Dar es Salaam, Tanzania. I bought a motorcycle. I rode the motorcycle for 6 weeks by myself all around the whole country, and went to
Oh
all the
my
national parks, and
God.
went to all these tiny villages. Like you can't get there by car, or plane. Like there are these really remote places. And it was freaking amazing. And it's like, you get in the habit of being like, oh yeah, I'm at MIT. Like, and there's a certain way you describe yourself to people in the world. And it gets
Yeah.
to be a little bit of a habit. We get used to like knowing how to describe ourselves. And, when I would say that to people there, if anyone spoke English, they're like, MIT, like what? Like, and
Who
I was like, yeah,
cares?
like Harvard. And they're like, huh? And and like then we'd like figure out that I was from the United States, and they'd just be like, "Oh, Obama land!" Like, yeah, because I guess Obama went to Tanzania, and so basically, it was the perfect way. It like totally, my goal was achieved. Like, no one cared about academia. Like, all
Yep.
of that was taken away, and it just comes down to what do you actually want to do with your life, and
Mm,
so that really helped. And I also like sort of use that time away, like, you know, thinking about whether, so I decided that I do want to go into academia, but I also decided, that I'm not going to let it like destroy my soul, because I had seen a lot of assistant professors come to MIT, and like within a year, no offense to any of my former
I get
professors,
it. Mhm.
but they kind of looked like crap after the first year. They were like not healthy and not happy, clearly. And I didn't want that to be me. So I kind of was like, I'm going to do this, but I'm not going to like sacrifice every relationship in my life in order
Right.
to be a professor. That's just not worth it to me.
Yeah, that is an excellent.
So then, yeah, I finished the trip. I sold the bike,
Yeah.
flew back, and then started my postdoc.
Wow. That is an incredible story. I mean, again, completely unorthodox because, I mean, how many, I mean, God, what, 95% of like, I mean, it's got to be some close to that of like people who do their postdocs pretty much go right after they graduate. Maybe a couple months, but like, maybe if that, who knows? But they certainly don't take any trips, right? So it's like, you're getting more world perspective. And I think that's
Yeah,
super important because, um, I mean, again, like we've been saying, like there's more important things. There's more life experience you got to get, and like even I'm only like a third year graduate student, and I even see within myself like, oh man, academia like it just consumes me because that's all you see all the time. Um,
mhm.
and it works great for some people. Some people like that atmosphere, but I know myself, like I would never want to get consumed by it, right? So, um, how
Yeah,
so you said whenever would you go there for 6 weeks, Tanzania? Like all over.
yeah,
Okay. Was it just Tanzania or did you see
all
other
over. I
African
went
countries?
like 5,000 kilometers. No, just Tanzania.
Okay.
I don't like border crossings. They usually tend to be violent and
Yeah, yeah. I know.
sketchy.
Yeah.
Um,
I'm trying to think where Tanzania is. Is
so
it
I stayed
Central
in
Africa?
Tanzania, but
Oh, yeah, pull up a
it's
map real quick.
East Africa. So it's
East
south
Africa.
of Kenya. So it's where the Serengeti is. So I went to
Okay.
Mount Kilimanjaro, the Serengeti. It has the world's deepest and biggest lakes. And yeah, it was just amazing. It was
Yeah.
beautiful. I hung out with chimpanzees. Like, I went to places that you cannot get. So there was one national park that I went to. You can only get there by helicopter or motorcycle. And I was the first person who ever went by motorcycle.
Wow.
So it was like,
Which one?
yeah,
Mikumi?
it
Nayari?
was pretty amazing.
I'm trying to. I'm like looking at a
What's
map of
that?
Tanzania. I'm looking at it. I'm looking at a map of Tanzania right now. Was it the
Oh,
Mikumi?
Mahalo.
Oh, Mahali. Okay.
Yeah,
Oh, that's okay. That's on the
Mahalo.
west. Okay, that's on the western.
Yeah.
That's on the western bank. How
Yeah,
did
it's
you
on Lake Tanganyika. It's the most beautiful.
How did you like get there? Because I know like, do you fly into Tanzania directly, or like where do you have to? I assume you got to fly
I
somewhere in
flew,
Europe, and then
yeah, I
you
had
flew
a
down.
flight. I got a flight. It was like $900 ticket. I think I had a layover in Turkey. And then, so all in all, the whole trip cost 2000 under $2,000, and most of
Wow.
the cost was for the national park entrance fees. The motorcycle I paid 1,200 US cash, and then sold it for 800. But I had crashed it a couple times, so it was a pretty good deal.
Wait, did you know how to ride a motorcycle before
um,
buying it? Like, that's
no,
beautiful.
I
No,
had taken
never.
the basic rider course
Okay.
in the US before so I planned all this. Like, I had planned it, and I took the basic rider course, but you don't leave second gear and you don't leave the parking lot. So the first time I actually rode a bike was in morning commuting traffic in Dar es Salaam, and it was
Uh,
like terrifying. Like, the most white knuckle experience ever. But then like, so I was just like gripping the steering wheel and just like riding out of the city, and it was like it was
That's
very
incredible.
tense because there's like bikes and ambulances and trucks and like people with like just everything, and then but then eventually all the villages like subsided, and then all of a sudden I was riding and this family of monkeys ran across the road in front of me, and I was like, holy shit, I'm riding a motorcycle
Oh
across
my
East
God.
Africa. Like, this is amazing. Yeah.
That is
it
absolutely incredible, actually.
it was a good celebration of
Oh
independence.
my God. You were just over there by yourself. Screw it. I'm going to buy a motorcycle and then just go like the
Yeah.
African wilderness and nature. Like, and I'm sure the people that you met
Yeah,
there,
pretty
like, it
much.
was
Yeah.
like, it's probably like, you
It's
couldn't even probably
amazing.
put into words like how like upgoing and upbeat these people are. Right. So it's like, I know like a lot of like
Oh
African
God,
people
it
that
was so
like,
amazing. Yeah.
that's good for you. That's incredible. Um,
Yeah. Well, and I didn't realize at the time, like women there don't even ride bicycles.
mm,
So like I didn't realize I would ride through these towns and the younger girls would just like watch me go by, like mouths open, like is that even possible? Like a bunch of these like teenage girls once came up to me at a gas station and were like, "Are you really a girl?" They were like, they didn't believe me that it was like actually physically possible.
That's awesome. How did you? I
Yeah.
guess one question I have about that, like,
Yeah.
how did you choose to go to Tanzania? Like, and I know people go to like, Zambia, Zimbabwe, South Africa, obviously. Why
Yeah.
Tanzania?
I did a bunch of research. So I it had so let's see a bunch of reasons. One, it's not in like a state of war. That's a good
Yeah,
one.
yeah.
Two, they have like the statistics on like rape are really much better there than I think in South Africa 1 in 3 women is sexually assaulted.
Yeah, that's pretty
And
messed up there.
Tanzania is like a place that people really pride themselves on solving their problems through words instead of violence, and
Mm,
has like good statistics for women in terms of violence. And then also it has a huge ecotourism. So I've always wanted to see, like, I hate zoos, and I've always wanted to see elephants and giraffes and zebra, like all the animals like out where they should be and
right.
where in nature. And so I've always wanted to go to the Serengeti, let alone ride a motorcycle across it. And Then they have all these awesome national parks. So they have ecotourism, and then it's also like, I guess in terms of religion, it's pretty it's about a third Muslim, a third Christian, and a third tribal religion. So it was kind of like this mixture of statistics that made me feel like this was a safe option. I mean, again, my family was horrified that I was doing this, but I had done research, and it and honestly, like, my travels there alone were way safer than my travels in the United States alone.
Hmm.
And I'm lucky, I'm sure, but like the even interacting with men, like I would just tell them like I had a boyfriend at home, and they would just like be like, "Oh, congratulations, that's really great for you," like, and
Yeah,
leave me alone, basically, which is
yeah.
not the case in the United States.
Well, I mean, we're so privileged over here, right? So it's like we take all this shit for granted over here in the United States. But um, yeah, that's incredible. It's definitely important to bring up too, because countries like the DRC, you don't want to go there right now with the internal wars that are going on there.
Yeah,
Um, Even like South Africa with like
yeah,
DRC, but also DRC, like the mining that goes there. I mean, um, precious metal mining. Same with South Africa. Like
yeah,
it's quite a shame, honestly. Like the mining that goes on there, and like the domestic or physical assault and sexual assault that goes on there is very serious. But there are
yeah,
African countries that are certainly travelable. I don't know if that's a word, but Um,
Yeah.
yeah, that's really cool that you did that.
Well, yeah, it was awesome. I mean, I think there's a ton of awesome places to go
Yeah,
in Africa. I recommend Tanzania. But yeah, like again, I don't think it's like by any means safer. A lot of places in the U.S. are way way more dangerous
right.
than
I was gonna say like even
like
like
it's
if,
not. Yeah,
it's like especially like if you're in like Chicago, LA, New York. I mean, is Africa or at least some countries in Africa really any less dangerous? Probably not. I mean, if you're walking down the streets of like New York, Chicago, I
yeah.
don't know. I doubt it. All right, so
Or
um,
even some like real rural places in the United States.
right,
There's a lot of hatred out there, and for
yes,
anyone who, I mean,
a lot of
you might be
prejudice.
okay, but they might
Yep.
still be like, what's the deal with your beard and your hair, but like it's just a hostile. There's a lot of hostile places in
Right.
the, globally, right? Like I don't. It's hard. I haven't been enough places to really assess, but I
Yeah.
certainly wouldn't say that the United States is safer.
Hmm. Yeah. That's yeah. That is an awesome experience. Hopefully, hopefully more grad students who graduate who are thinking about doing a postdoc, maybe they'll listen to this and take a trip for themselves and like get out in the world because academia shouldn't consume your life. Please, like, don't let it consume your life. Like, get some life experience before really kind of committing to that. Um, but
Well,
any,
I think it so like I guess for me, and I think
yeah, yeah,
everyone's different. You got to find a whole balance. But like I
fair.
like it to consume my life, but I just want to be I can do one thing really passionately and totally all consuming, but I can also do multiple things like that, right? So like I
Mm,
also have other things that I'm passionate about. And that doesn't mean I have to be less passionate about my job and my career because I also have another passion. Like I have a pretty unlimited boundary. Like it's not like there's a maximum amount of passion you're allowed to have.
right.
And you have to balance, you have to choose how much you're going to give to chemistry and how much you're going to give to what your other hobbies are. So I
Yeah.
guess I would say I do feel all consumed with my career, but I'm also all consumed with other parts of life too. So,
Yeah, that's a great perspective. That's great. That's a great point. Um, but anyways, I definitely want to get to your research. You're doing research now. But just briefly on your postdoc, so you went to UC Irvine. What did you work on there, and who was your advisor there?
yeah, so I worked with Andy Borovic and I
Mm,
made artificial metalloproteins
okay.
in his lab. And um, so I kind of classify artificial metalloproteins into two general categories. And so for anyone who hasn't heard of these, they're proteins that don't natively have a metal binding site, or maybe they have a metal binding site and you manipulate it through site directed mutagenesis. You somehow modify it in some way, or you add the metal binding site that didn't exist before. Um, and these have been used both for directed evolution to evolve new catalysts. And they've also been used to model enzyme active sites. And so, Andy has really spent his career, studying the hydrogen bond and the impact of the hydrogen bond on coordination complexes. And synthetically, it's really challenging sometimes to install a hydrogen bond exactly where you want it without affecting the other properties, like the electronic properties of the metal ion itself. Because the ligand is all attached, right? So if you synthesize a ligand with a dangly bit here, it's also, you had to modify it somehow chemically, and it's going to impact the actual redox potential of the metal complex and other properties, or of the metal center itself. And
Mm,
so using artificial metalloproteins, you can use site directed mutagenesis. So you install your metal complex, and then you can make an amino acid mutation over here that installs that dangling hydrogen bond, or you can change the electrostatic environment and other things. And so basically the two categories I kind of put artificial metalloproteins into are for evolution of catalysts or for modeling, like structure function correlations type thing, where if we can model the effect of a hydrogen bond and have the complex with and without it and see how the properties differ, we can then make comparisons to what's known about actual enzymes that have hydrogen bonding interactions in their active sites. So that's what I did. I worked on that stuff. I made made artificial metalloproteins. I got his lab started doing protein purification and expression and purification in his lab. I learned some protein crystallography and some more inorganic chemistry. And I
was gonna say, it sounds like, because I mean, this is basically what you do now. I mean, you do switchable artificial metalloproteins, so it kind of really set the stage, I guess, for what you like to research, your research interest now at UI. So I guess let's get into that with some time that we have left here. So, your research interests are, like we mentioned, switchable artificial metalloproteins, but also, I mean, really studying like conformational changes within these proteins, I think, is kind of the core, I guess, of your research interest. And so perhaps maybe we could start with, we'll start with this. How about the switchable artificial metalloproteins? Because I think that you guys kind of develop conformationally switchable metalloproteins, and that kind of serves as a model to understand like the macroscopic structural changes and let's say the subatomic electronic structure. So obviously this is something you've been interested in since a postdoc. So how far has this kind of project come for you guys?
So I'll actually, let's see. So it actually all started kind of as a grad student. And so, you know how I was saying that ribonucleotide reductase it's conformationally gated. It means that the slow step, the rate determining step in catalysis, is a protein structural rearrangement. I kind of became obsessed in grad school with how that protein structural rearrangement then triggers proton coupled electron transfer through the enzyme. Mm-hmm. And you asked me earlier if there were any like big findings during my PhD, and I didn't talk about so there was one experiment that was probably the most surprising and cool experiment I've ever done in my life. And it sowed the seed for both a bunch of stuff that they're now doing with ribonucleotide reductase, and also for my own independent career, which is that, so I said RNR, ribonucleotide reductase is abbreviated RNR. So RNR has these two halves. So you're asking, how do I pair it? I have to purify these two halves. Those two halves come together during catalysis and then they come apart. And it happens, it's pretty fast. It's a pretty dynamic process. It turns out, so when they come together and substrate binds, an electron / lack of an electron so an electron is transferred from this half to this half while they're together. Yep. And then catalysis happens, and then the electron is transferred back to its starting half, and then they come apart. And it's electron and a proton. What we discovered, so my lab mate, Ellen Manhan, she had this hypothesis that, so she was installing unnatural amino acids into this PCET pathway through the enzyme. And she realized that when she puts an amino tyrosine, which has a lower redox potential than tyrosine, she could trap the hole, basically, so that, they come together, electron goes from this half to this half, but then it gets stuck in that half. And what she discovered is that when that happens, the electron doesn't return and they don't come back apart, or they come back apart much slower. And I guess the experiment, so I was doing these fluorescence experiments where I was doing stop flow spectroscopy and looking at the rate constants for this complex to dissociate. And we did it with her aminotyrosine variant, and they didn't come apart on the stop flow time scale. And it was so crazy because so you have this whole super complex. It's a huge, complicated enzyme, but just because one electron is stuck over here, this whole thing just gets trapped in time and space. It just stays in one place because of one electron. And you cannot chemically, you can't like take this half and chemically reduce it with an electron and then this thing sticks together. It has to be that the electron came from over here and goes over here. So this is just like mind blowing to me. And it's actually that discovery that led to them more recently, or, that and a lot of other people's amazing discoveries. But like this same concept where you could trap the active complex was applied to actually obtain the first cryo-EM structure of the whole thing altogether. Before we had no idea what it looked like when it was all together. And a bunch of other really cool stuff that they're doing now. But that link between protein conformation and these, the transfer of a single electron is just something that I'm still trying to understand. And it's really kind of the focus of my research. However, instead of studying one of these natural systems, these really complicated enzyme systems, we're making simplified models for how protein conformational changes can dictate electron and proton transfer and changes in, triggered changes in a metal or a metallic cofactor state or the properties of it. And so that's kind of where all my research is inspired from. And we're making these models where we're trying to trigger a conformational change and then look at the effects on the metal complex or the metal ion that's inside. So in one of our systems, we're using light. So we made photoactivated ligands that when you shine light on them, they twist. And we're using these for copper complexes that, copper 1 and copper 2 have very distinct coordination preferences. Typically, copper 1 will want to be tetrahedral, while copper 2 will be tetragonal. And so we're basically photo triggering these different structural changes to try to manipulate electron transfer rate constants at copper. And then in our artificial metalloproteins, we're using a protein that undergoes a big structural change when a small molecule binds, and we're installing a metal complex inside of that protein so that, when allosteric, I don't know what I'm doing with my hands, when the allosteric binding event happens at one site, then the properties of the metal complex change over at this other site.
Okay.
And that is just mimicking this mechanism that is not just in ribonucleotide reductase, but is in the majority of enzymes. The majority of enzymes have their rate determining step for catalysis is a conformational change. Okay. And understanding the link between these big, slow protein motions and how they actually control catalytic steps down to one electron is like the goal of my lab, to mimic that, to understand it, and then to apply it for various purposes, like solar energy conversion or bioimaging, different and drug delivery, things like that.
That's incredible. I have a couple questions. One is understanding. So copper 1 likes to be tetrahedral, but then I guess when you photo induce it, it goes to a different shape to copper 2. Do you guys understand the reason for that? Like, I'm not really familiar with like conformational changes. Like, is there?
Well, so it's really that copper 2. So copper 1 has 10 d electrons, and so it basically has no electronic preference for one geometry over another. And so all things being equal, sterics will predominate and dictate that it'll preferentially adopt tetrahedron if it's 4 coordinate, which minimizes the steric interactions. But as soon as you take one electron out, those d orbitals. Then you have what's called the Jahn-Teller distortion, or a structural distortion, which results in a more energetically favorable coordination geometry. And so it's for this reason, it's because, so the copper 2,1 redox couple is usually associated with really large structural reorganizations, which leads to slower electron transfer rate constants, based on Marcus theory, where the more structural reordering that you need to do going from the reduced to the oxidized state, the slower the electron transfer rate constant will be. And so we're basically trying to use light to, like, instead of having to reorganize the coordination geometry, we're trying to use light and a photoactive ligand to pre-organize it in order to control, to have fast electron transfer, even though it has to reorganize, or even though it has these different structural preferences.
Right. Okay. That's. I guess another question I have on that is then you'd mentioned that you're using kind of you're making artificial metalloproteins. So are you able to, like, simplify? Because I assume you're not using like an entire, like, protein structure, because they are ginormous. So, like, where are you kind of allowed to take shortcuts with designing these artificial proteins? Like, is there like a point where it's like, okay, this is actually just, we've shortened it just enough so that still it kind of mimics a metalloprotein, versus like, no, we're something completely different. You get what I'm saying? Like, I don't know, like, what the cutoff is for these kinds of systems.
Yeah, well, so we're choosing, so there's all different sizes of proteins, and we're choosing small, simple, stable ones.
Fair.
And so that's, the starting point. So for them, we've been working with periplasmic binding proteins, which are very simple, and they basically have like this Pac-Man thing where they just they'll bind some small molecule and then just chomp down. It's a very simple conformational change, and they're structurally, a lot of them, they have crystal structures, and they can withstand a lot of different conditions. And so that's our protein host. And then we're installing synthetically prepared metal complexes inside of those.
Okay.
Yeah. So it's not, so we are trying to make simplified models, but also I don't, you may think like, oh, it'd be simpler to just synthesize some big organic thing, but it's actually pretty hard to design molecules that can do a simple conformational change.
Sure.
And so that's why we're using these simplified proteins.
Yeah, that makes sense. Yeah, I mean, and like,
then of course we can use the mutagenesis strategy to modify. So like in the open state, you have the metal is in one environment, and then when it's closed, you can put in amino acid mutations that, for example, add a hydrogen bonding interactions to around the metal complex to, like, because we know those hydrogen bonding interactions will change the properties of the metal. So then the closed state has a distinct set of properties.
Yeah. And the brief understanding that, I have about biological systems is that, like, it's really like a lot of the conformational changes that really are kind of dictating like all these biological events, right? So it's actually like, it's really not, I mean, obviously, like I forget what it's called, but like where the main source of, I guess, where the conformational changes aren't like the direct, it's actually the allosteric interactions that are also extremely important in these events.
Yep.
So
exactly.
I hear that.
And it's still not, in a lot of cases, understood how, some allosteric binding energy, like the allosteric event, may be exothermic. It may release some energy, but then how is that energy converted to the active site? And I basically think that that proteins use these triggered structural changes to do more efficient energy conversion, where like in industry and in synthetic systems, we just heat things up.
Right. Okay.
But that's not a very efficient way to convert energy. You lose so much thermal energy when you just heat everything up. Whereas these allosteric events, it could be like a couple kcals, but that gets transferred from an allosteric binding event to the active site, and that's enough to turn on catalysis. So
Right.
it's really, I think, one way that enzymes are able to operate at like constant temperature and constant pH, and you can't, they're under mild conditions.
Right. And they've also had like millions of years to do all these things, and we've only been studying it for God knows
Yeah.
like 30 years to trying to synthetically understand these things. So I think that's something to keep in mind as well. How did you? Other question I had is, how did you kind of decide to study these like copper systems? I mean, I don't know if you're doing any other like metals that you're interested in, or was it just kind of like these are kind of the easiest systems to at least get started on? Um, yeah, I don't know. How'd you decide those?
So copper is definitely not too easy, but it was because of this very distinct and established coordination geometry preference for the two oxidation states.
Okay.
And because, if we want to use a conformational change to modify the properties around a metal complex, that metal complex needs to have some dependence on conformation.
Mm.
And we wanted, so you can change the redox potential of a copper center by how much it's twisted, and there's other systems like that, the nickel, there's other examples that we're exploring, but copper was just an example of a metal center that has distinct coordination preferences for its two, depending on which oxidation state it's in.
Right. That's awesome. Well, as we begin to wrap up here, I guess the one other thing I wanted to ask you is, what can a graduate student expect to learn within your lab? Like what techniques, what ongoing projects are you trying to learn, et cetera, et cetera.
Yeah, it's a great question. We're a super interdisciplinary lab, so obviously, like as like a initially I was like a synthetic chemist, and then I joined an inorganic lab, but then I collaborated with a biochemist and did time resolved spectroscopy. We do kind of all of that stuff. So we do
Fair.
synthesis, we do inorganic synthesis, organic synthesis, all the characterization that goes with that, X-ray diffraction and ECAM and UV, all of that, Mossbauer, EPR, squid, all these
Moss
things.
power.
Yeah. And then we also do time resolved spectroscopy. So we have a transient absorption spectrometer and, look at these transient processes. We do other kinetics techniques like stop flow. And then we do protein expression, purification,
Oh boy.
mutagenesis, bioconjugation strategies to work with these proteins and then to characterize those. So we do protein X-ray diffraction, and we use a bunch of biophysical techniques like isothermal titration calorimetry or CD spectroscopy. Um, and Again, then spectroscopy. I mean, the great thing about working with metals is they have these very distinct signatures depending on their coordination environment, their oxidation state, and so we try and basically correlate those properties with the changes in the three-dimensional structure that we're triggering. So it's super interdisciplinary, and we really kind of take projects. There's these fundamental aspects of questions that we want to answer, like by modeling these conformational changes, what can we then say about actual enzymes? But then in the process, we're also making a bunch of switches, molecular and protein switches, which are super useful. So we're applying these, like I said, for developing new MRI contrast agents that are going to detect early diseased states by measuring actual analytes in the body instead of just imaging tissue, like tissue mass or tumors, basically. And we're working on with these copper systems generating long-lived charge-separated states to use in solar energy conversion. For eventually, we'd like to hopefully apply these to direct solar to fuel conversion.
Yeah.
But it's definitely a work in progress.
Yeah, that's exciting stuff. I look forward to seeing what comes out of your lab over the next, well, hopefully a long time, honestly. But yeah, I definitely could say, I mean, this is definitely on the front end of interdisciplinary. I mean, just listing all the spectroscopy techniques, I mean, God. And then plus on top of that, trying to purify like metalloproteins or artificial metalloproteins, like that is some hardcore biology, and then but also like hardcore like inorganic spectroscopy chemistry. So you really are in the front lines of those two fields, which is really cool and unique to see.
My
Really,
students
honestly,
are pretty amazing.
But yeah, with that, I want to thank you,
Thanks.
Professor Olshansky, for joining me today. It's super pleasant talking with you. And then I don't know. Hopefully, I could see you at a conference sometime soon. We'll see. But
yeah, that'd be awesome. I love conferences, so we should definitely talk science sometime.
If I ever find myself in the cornfields of Urbana-Champaign, maybe we'll stop by the lab and check it out. So, but with that,
awesome. Yeah, it's actually a pretty cool town. I gotta say, I'm surprised, but yeah.
My advisor, Brad Carey, he did his graduate degree with Hartwig at when he was at Urbana-Champaign at the time. Okay. So, seems like, I mean, it's great. I mean, it's a great science school. It's a great chemistry school for sure. So
it's a great science school. It's a fun little quirky, artsy town too. I think there's a lot more here than people realize at the outset. But
try and keep it secret so no one knows about it. Keep it keep it on the revs.
Scientists to come here. And
all right, well, fair. No, but all right. Well, I want to thank everyone for another episode, and we'll see you on the next one. Alrighty. So I think something went wrong.